Sir Humphrey Davy discovered several elements including sodium, potassium, magnesium, calcium and strontium. Part A. Explain which block in the periodic table sodium and magnesium belong to. Sodium and potassium are in the S block of the periodic table. The reason for this is because their highest energy electron is in an s orbital. So to get the mark for this question, we need to say that they're in the s block because the highest energy electron is an s orbital, hence why they're s block elements. Part B. A sample of magnesium Ar 24.305 is found to consist of 3 isotopes. The accurate relative isotopic masses and the percentage abundances of 2 of the isotopes are shown in the table. Determine the relative isotopic mass of the 3rd isotope of magnesium in the sample. Give your answer to 5 significant figures. To work out Ar, you multiply the relative isotopic mass by the percentage abundance and divide by 100. So for this sample, that would be 78.99 multiplied by 23.985 divided by 100. And then we need to add the next multiplication or the next calculation that we're doing. So the relative isotopic mass times by the percentage abundance over 100. So that would be 10.00 multiplied by 24.986 divided by 100. And then to work out the 3rd isotope, that would be, we need to do 10.00 plus 78.99. And then all of this, we do 100 minus, and that gives us the percentage of our 3rd isotope. And that would be 11.01. So what we do in the fraction is we have 11.01 multiplied by m divided by 100, and that is going to equal 24.305. Rearranging this equation, we then get 11.01 times by m divided by 100, and that would be equal to 2.860645. And then that makes 11.01 times m equal to 286.06485. So then making m equal to 25.982, and that is to 5 significant figures. And I'm writing it to 5 significant figures because that's what we're told to do in the question. So then on the answer line, we need to write 25.982. For this question, you get your first mark for writing your fractions and that they're equal to the Ar of your sample of magnesium. And then you get your second mark for working out the relative isotopic mass of your 3rd isotope, and that would be 25.982. Writing this to 5 significant figures, that all gets you your second mark for this question. Part C. A student adds an excess of calcium oxide to water in a test tube. In a separate test tube, the student adds an excess of strontium oxide to water. Part 1. Write the equation for the reaction of calcium oxide with water. State symbols are not required. Calcium oxide has the formula CaO, and water has the formula H2O. So these would be the formulas of our 2 reagents. And then we're going to produce calcium hydroxide, which has the formula Ca brackets OH brackets 2. And now we've balanced the equation. We've got 1 calcium on both sides, we've got 2 oxygens on both sides, and 2 hydrogens on both sides. To get the mark for this question, you need to write the equation as I've written on the screen here. The formula of calcium hydroxide is as follows, because if we use the crossover rule, calcium has a 2+ charge and OH has a minus charge. So crossing over, we would have Ca1, because it's 1 minus, that means 1 calcium, and 2 OHs, because we've got a 2 plus charge from the calcium, meaning we need 2 negative charges to counteract this. Part 2. Suggest the appropriate pH of the 2 solutions formed in the test tubes. With group 2 oxides, such as calcium oxide and strontium oxide, we associate their pH with being basic, and also the reactivity of group 2. So the reactivity of group 2 elements with water, or group 2 oxides with water, they become more reactive as you go down the group. So as they become more reactive, they're going to become more basic or have a higher pH. So for calcium oxide, this is still quite a strong base, so we can give it a pH of 12. For strontium oxide, this is going to be slightly higher because it's more reactive with water. So in the equation we did above with calcium oxide and water forming calcium hydroxide, the formation of strontium hydroxide, this is going to be a faster reaction because it's more reactive. And so it's going to be more basic and have a higher pH of 13. For this question, you get a mark for saying 12 and 13, or having the pH of strontium oxide as higher than calcium oxide. And also ensuring that both pHs are basic or above 7. These 2 things will get you the mark for this question. Part D. The table below shows enthalpy changes involving potassium, oxygen and potassium oxide, K2O. Part 1. The incomplete Born-Haber cycle below can be used to determine the lattice enthalpy of potassium oxide. In the boxes, complete the species present in the cycle. Include state symbols for the species. For this question, we're going to start in the bottom left. And the equation we're going to write is 2K as a solid plus half O2 as a gas. So then we're going to label the equations, or the arrows, either side with their relative enthalpy change. So the arrow going down, this is the formation of potassium oxide, so that would be minus 363. And the arrow going up, this is the atomization of oxygen, because oxygen is going from half O2 to just an O as a gas. And then we would label this as plus 249. Continuing with our next equation, we would have 2K as a gas plus O as a gas. Now labelling the arrow, or the equation, or the relative enthalpy change. So what we're doing here is the enthalpy change of atomization of potassium. So labelling this arrow, that would be plus 89. And because there are 2 potassium atoms, we need to multiply this enthalpy change by 2. Labelling our other arrow, that's the first ionization energy of potassium, because we're forming a K plus ion. So that means we're going to label this plus 419, and we're going to multiply by 2 again because there are 2 potassiums involved. Following the cycle around, our next equation, we're going to have 2K plus as a gas, and then we're going to have an O minus also in a gas state and 1 electron, because what we've done is we have conducted the first electron affinity of oxygen, where we've made oxygen have a negative charge. So labelling this arrow, we would label it as the first electron affinity of oxygen, and that is minus 141. The last equation we need to complete this Born-Haber cycle is our 2K plus gas plus O2 minus in the gaseous state also. And what we've done here is we've done the second electron affinity of oxygen, which is plus 790. And what we've done is we've converted the oxygen with a negative charge to the oxygen with a negative 2 charge. So here we've labelled all the different parts except this big arrow along the right hand side and this big arrow along the right hand side. This is what's known as the lattice enthalpy. So we can label this as delta H because we're going to be asked to calculate it in the next bit of the question. Part 2. Calculate the lattice enthalpy of potassium oxide. For this question, we need to refer back to our Born-Haber cycle. So what we're trying to work out is what I've labelled here as delta H. This is the lattice enthalpy of potassium oxide. So one way to work it out is if we went round the cycle. So we would go down here and then up and then all the way down here. And that would create this arrow that we're trying to work out. It's just a different way of calculating it. So what that would be is if we did minus 790 plus 141. So what I'm doing here is if the arrow is going in the opposite direction, I'm changing the sign. So then we would have minus 2 times 419, then minus 2 times 89. Then we're going to minus 249 and minus 363. So this would produce our lattice enthalpy, and that gives us the value of minus 2,277 kilojoules per mole. So then we need to write this value as our answer, so that would be minus 2,277 kilojoules per mole. To get the 2 marks for this question, you get a mark for getting this correct answer, so minus 2,277, but you also get a mark for your first line of working out. So this is this line of working out here, which is where you've worked around the Born-Haber cycle in order to find your answer. Part E. A similar Born-Haber cycle to potassium oxide in D can be constructed for sodium oxide. Part 1. The first ionization energy of sodium is more endothermic than that of potassium. Explain why. The first mark for this question comes from saying that for sodium, its atomic radius, it's important we specify that it's the atomic radius and the fact that it's smaller. And so our second mark comes from saying that its nuclear attraction is therefore going to increase. So now if we delve a bit deeper into why this causes the reaction to be more endothermic, well, the reason for this, by the way, this won't get you marks, but it's important for your own understanding of the topic. So what happens to make the first ionization energy of sodium more endothermic is because there's a stronger attraction to the outer shell electrons in sodium, and that makes the reaction more endothermic because it's going to require more energy to remove this electron because of the stronger attraction. So this is why the first ionization energy of sodium is more endothermic. Part 2. The lattice enthalpy of sodium oxide is more exothermic than that of potassium oxide. Explain why. The reason why the lattice enthalpy of sodium oxide is more exothermic than that of potassium oxide is because sodium ions have a smaller ionic radius. Because they've got a smaller ionic radius, the Na+ and O2- ions have a stronger attraction because there's less space between them. To get the 2 marks for this question, you get your first mark for saying that sodium ions have a smaller ionic radius, and your second mark for saying that Na+ and O2- ions have a stronger attraction. The comparison of ions is essential to getting the mark for this question. And also you can't say small, you have to say smaller when talking about the ionic radius of sodium ions, because this is what they mean by comparison. And that's what they want you to do for this question, is compare.